All right, good day, everyone. Now, in the process of using R, or in the process of learning R, we've been using symbols like this arrow symbol, the plus symbol, dash, the asterisk, the forward slash, and even the caret occasionally. And we've also learned that in the R language, these are what we refer to as operators because they're quite literally used to perform operations like assigning a name to an object or adding numbers together or subtracting numbers, etc. But there is a somewhat more unique category of operators called relational operators. And what these allow you to do is evaluate a comparison of some kind. So, as an example, recall that R has a built-in constant for pi. So if you type pi in your script window here and you run that, you can see you quite straightforwardly just get, the first few digits of pi. But what we can do is we can use a relational operator to ask if a certain number is maybe greater than pi. So we could ask, is 3 greater than pi? And we could run that, and you can see that R tells us that this statement that we've just written is false. So you can see R is returning a logical value here. And in all cases of relational operators, that is precisely what's going to happen. We could alternatively have asked, is 3 less than pi? And if you run that, R tells us that this is a true statement. In other words, yes, 3 is less than pi. In a similar fashion, you could also evaluate whether a value is greater than or equal to some other value. So for instance, is pi greater than or equal to pi? So you could say pi greater than or equal to pi, like so. And R evaluates that as a true statement. Alternatively, you might choose to evaluate whether a value is less than or equal to some other value. So we could ask, is pi less than or equal to 3? And if you run that, you can see it spits out a false, indicating that pi is not less than or equal to 3. You could also evaluate whether two numbers or two values are equivalent or not equivalent. So for instance, if we want to test whether pi is exactly equal to itself, we could say pi double equal sign pi. And if you run that, you can see it spits out a value of true. Alternatively, as another just sort of example here, 22 divided by 7 is often used as a kind of simple approximation of pi. So if you divide 22 by 7 and you look at that number, you can see, just kind of at a superficial glance, it looks very similar to what pi is. So we could write some R code to ask if these numbers are exactly equivalent. So we could say pi double equal sign, and then we could say just simply 22 divided by 7. And if you run that, you can see it says it's false. Now notice the distinction here between the use of a single equal sign and two equal signs. Okay, so in R, when you use a single equal sign, what you're doing is you're assigning a name to an object. So if we type something like A equals 1, what we've done there is we've just assigned the name A to this object 1. So if we run A, you can see we get a value of 1. However, when you use a double equal sign, like we've done here, you're asking whether one object is exactly equal to another object. And the answer to that question is obviously going to be either true or false. So for instance, we could ask A double equal sign 2. And if you run that, it spits out a false. Lastly, you can also evaluate whether two values are not equivalent by just simply using an exclamation mark. So we could ask pi exclamation mark equal sign 3. So this spits out a value of true, and the reason it spits that out is because this statement we've written, or this expression, is asking if pi is not equal to 3. So the little exclamation mark here can just be interpreted as not something. So in this case, not equal to. Now, before we leave this topic, there's one thing you should be aware of. So let me just get rid of that. In almost all cases, Numerical values in R are represented inside its memory as doubles. So what that means is, you know, what that means is these are values that have their numerical calculations handled by something called floating point arithmetic. So the thing to remember about computers is they only have a finite amount of memory to actually store numbers. And floating point arithmetic basically offers them kind of a nice compromise between precision and memory usage. The drawback, though, is that they can lose precision with really large or really small numbers. And for safety, you should basically always think of doubles as approximations of real numbers as opposed to real numbers themselves. So, to sort of illustrate what I'm talking about here, consider this. Let's say we take 0.9 and we subtract 0.5, and you run that. So you can see we get 0.4. Makes sense, right? So if this is equal to 0.4, then logically, this statement that we write here, so if we write 0.9 minus 0.5, we say double equal sign 0.4, logically, this statement should be equal to true, right? So if you run that, you can see, yeah, R is saying these two things are equal. Makes sense. But let's try a different set of numbers. So let's try 1.9 minus 1.5. Run that. You can see, oh, look at that, 0.4. Logically then, if we do something similar to what we did there, so we say 1.9 minus 1.5, so double equal sign 0.4, and we run that, this should be true. But it's false. Why is it false? This doesn't seem correct, does it? And, mathematically speaking, it's not correct. But the computer here is not wrong to say that this expression we've written is false. And the reason it's not wrong to say this is because from its perspective, both sides of this expression are not the same. Basically, because of the computer's use of floating point arithmetic, 1.9 minus 1.5 is almost zero point 0.4, but not quite. So this earlier 0.4 that it output is really just a rounded version of what the computer understands the result to actually be. So if you want to see how R actually understands kind of this number that we're looking at, what you can do is you can simply tell R to display all 16 digits that it's calculated. So what you could do is you could type options and then say digits like so, and just set that to 16. Run that, and now if you evaluate this expression, you'll see what R actually understands this number to be. So if we go 1.9 minus 1.5, and you run that, you can see it's not quite 0.4, but it's pretty darn close. And I think it's worth emphasizing that what we're seeing here is not a problem that is exclusive to R. This is really just a limitation of computers generally. The same limitations we're seeing here are going to be encountered in other programming languages like Python, for instance. The key difference, though, with R is that it will, by default, display, the numerically correct value of 0.4, whereas something like Python is just going to show you this, or something like Python is just going to show you this big nasty 0.3999999, etc. And depending on your own personal philosophy, you might think that's a smart thing for your programming language to do, or you might think that's a dumb thing. It really kind of depends on who you're talking to.